Today's video we're going to be looking at particle physics, and now this will be quite a long video because particle physics is a big topic and it all links together just like a puzzle, so make sure you use the timestamps at the bottom or stick around to the end of the video so it can all kind of make sense for you. So all matter, to start off with, can be split off into two subcategories, either leptons or hadrons. Now hadrons are not fundamental particles, we'll come on to them later, but leptons are, and I guarantee you'll know a couple of them already. So leptons, the main lepton you've come across before is the electron. So the electron has a negative charge. We signify that by the little negative symbol here. In the lepton family, we also have muons and tauons. Now muons, we come across where they are types of cosmic rays coming down to Earth. They're about 200 times heavier than the electron, still have a negative charge. Tauons are even heavier, but we don't come across those at A level, but it's useful to know they're there. Also in the lepton family we have the neutrino, which has this symbol nu. The symbol for it's kind of like a curly V, and they come in three flavours. Yes, that's right, flavours. They come in electron, muon or tauon flavours, and they are neutral as the name suggests, so they are the only uncharged lepton, and they are incredibly small. They are virtually massless, and that means they are very, very difficult to detect. It takes a lot of effort to detect one. They very rarely interact with matter. So how do we know they exist? Well, they are hypothesized in beta decay. So beta decay had a big problem, which was that when the neutron changed into a proton and released a beta particle, if you add together the energy of the proton and the beta particle, you end up with less energy than was initially locked up inside the neutron. So the hypothesized particle was thought up by Paul Dirac to carry away that extra energy, and they knew it must be neutral. They knew it must be very, very, very small mass, because otherwise it would be found it already, and they hypothesized it was the neutrino. Now in this instance it's an anti-neutrino, which is an antiparticle. We'll come on how we know that a little bit later, but it's a good excuse to look at antimatter and antiparticles early on. So all these leptons have antiparticles. So we have antineutrinos, as we've discussed. We have an anti-electron, which is called a positron. We have an anti-muon and anti-tauon. And for their symbols, you might have noticed the negative sign changes to a positive sign. So that gives us a big clue into what antiparticles are, which is that they have the opposite charge to their regular particle counterparts. So a positron is exactly the same as an electron, apart from it now has a positive charge. Everything else is the same, so it'll have the same mass, the same, like every other characteristic about the particle will be the same apart from the charge, which makes it an antiparticle. Let's look at where we might find this positron being emitted. It actually gets emitted in something called beta plus decay. So in beta plus decay, instead of a neutron changing to a proton, we have a proton changing to a neutron, and then a positron or positive electron is emitted along with a regular neutrino. Now, something very interesting happens when you have a particle and its antiparticle meet. So, for example, it could be an electron and a positron. Now, when they meet, when they come together, they cease to exist. It's absolutely mad to think about, but two particles can just basically disappear. That process is called annihilation, and it doesn't just disappear into nothing, but it disappears into energy. So, in annihilation, the matter inside the particles is converted to pure energy in the form of waves. We could say the mass is converted to energy, and that is given by E equals mc squared, which we'll do a calculation with later, but E is energy and m is mass. So let's have a look at a specific example then. So let's say we have an electron meets a positron, they meet with a significant amount of energy head on, and these two gamma rays are emitted up and down to conserve momentum. So we can calculate the energy that these photons are going to have due to what's called the rest energy of the electron and of the positron. Now the rest energy, to define a key term early on, as the name kind of suggests, rest means no velocity, so rest energy is the energy locked up in a particle's mass if it was all converted to energy via E equals mc squared. So these particles might have kinetic energy, but the energy we're looking at here is the energy if you were to convert all of their mass straight into energy. So c in this equation is the speed of light, so c squared will be 3 times 10 to the power 18 squared, and an electron volt here, if you don't know, a mega electron volt is equivalent to 1.6 times 10 to the minus 13 joules. That's the conversion we're using here. So to work out the energy of each of the gamma ray photons, and we can also work out the frequency of each, we will need to multiply the rest mass by 2, because we've got 2 of those particles, same rest mass for both, which gives us 1.022 mega electron volts. And we've got 2 gamma photons that are emitted. So for one of those photons, we need to then divide by 2 again, which gives us 0.511 mega electron volts, the amount we started with. Now, we can also work out the frequency of the photon, because a photon is part of the electromagnetic spectrum, and we can work out its frequency. So the equation to do that is E energy equals hf, where h is a constant. It's known as Planck's constant. It's a very, very, very small, tiny constant, which is 6.63 times 10 to the power minus 34. So to work it out, very easy equation, we could just do the energy in joules. So we'd use that conversion factor over here, and then divide that by Planck's constant to find the frequency, usually quite high, because obviously gamma photons are the highest frequency of the electromagnetic spectrum. So if we can convert mass to energy, could we also convert energy to mass? Well, yes, we can. The opposite of annihilation also has its own name for converting pure energy in the form of a gamma photon into 2 particles, a particle-antiparticle pair, just like we see here with an electron and a positron. So this is known as pair production, which kind of sounds like what it should be, pair production, producing a pair of particles, one anti and one regular particle. This occurs when a photon has enough energy, so it needs to have above a sort of threshold energy for this to happen. So to work out the minimum energy that the photon would need, you'd need to know the rest mass of these particles. Now, we're using the same 2 particles, but before, it could be anything. It could be a proton and an antiproton. But anyway, you need 2 times the rest energy of one of those particles, which is 1.022 mega electron volts, and then convert it to joules, which gives us 1.64 times 10 to the power minus 13 joules. So that's the minimum energy the photon would need. You could work out the frequency again by using the same equation as earlier. That's it for leptons for now. Let's have a look at the right hand side of this diagram and have a look at the hadrons. And so hadrons can be split into 2 subcategories, baryons and mesons, but even these are not fundamental particles. They're all made from these things called quarks, which to the best of our understanding are fundamental particles, meaning they cannot be broken down into something smaller. So what are these quarks then? Well, these come in different flavours as well, just like our neutrinos. Now the flavours are up, down, strange, and you can also have top, bottom, and charm quarks. Now, luckily for you at A-level, we're only dealing with 3 quarks, so we're not dealing with top or bottom or charm quarks. There's loads of history and interesting things you can learn about them, but they're not on the A-level spec. We need to know about up quarks, down quarks, and if you do AQA, you need to know about the strange quark as well. So first thing to note is that the key information I'm going to write down here, in terms of their charge, is all on your data sheet. So charge of each quark is fractional. The up quark is positive charge plus 2/3. Down and strange quarks both have a charge of minus 1/3, and we introduce this thing called strangeness. So up and down quarks have no strangeness, we don't need to worry about it, but strange quarks have a strangeness, and it's even stranger than that. They don't just have a positive strangeness, a strange quark has a negative strangeness of -1. These quarks also have antiparticles, so we signify that by drawing a little line above the top of the symbol. So U, D and S now have a line above them to signify they are antiparticles. Now, as from earlier, the only thing that's different about an antiparticle is its charge. So the negatives become positive and the positives become negative. The strangeness of an anti-strange quark is also opposite. It is +1 strangeness. Now, something else we need to know about these quarks are their baryon number. So baryon number is another quantum number used to define these particles, and we'll come on to looking at why it exists in a second. But for now, the baryon number of all 3 quarks is 1/3, so 1/3. Now, protons are hadrons. They are also baryons. So we're going to figure out what quarks are inside a proton, because a proton isn't a fundamental particle. So we know that a proton has a baryon number of 1. It is a baryon, so therefore it's got a baryon number of +1. We know a proton's got a charge of +1 and no strangeness. So what quarks could be inside? Now, if you're ever asked to figure out what quarks are inside something, it's kind of a bit of trial and error, just figuring out one stage at a time. And now, we usually look at the charge first. We need to get a charge of +1. So we definitely need some up quarks in there. If we put 2 up quarks, that gives us a charge of +4/3. So therefore, we put a down quark in it, gives us -1/3. Can't be a strange quark because it doesn't have any strangeness. So inside a proton, we have up, up, down. Let's then take on a neutron, which this time is a baryon, so baryon number of 1, has no charge and no strangeness, so we need to get a charge of 0. So if you put positive 2/3 an up quark, we would need 2 down quarks to make the charge be 0. So positive 2/3 minus a third gives us 0, no strangeness, but it's 3 quarks, so therefore its baryon number is 1. Now let's take a lesser known particle, a sigma particle. Now in exams they could give you particles that you haven't heard of, but you'll always have enough information to figure out what they are. This sigma particle then, bit of a weird one. It has a negative charge, so a charge of -1. It also has a strangeness of -1, but it is a baryon, meaning it has 3 quarks in it. So what could be inside this then? Let's do a bit of trial and error to figure out what it must be. So we've got a combination of U, D and S. We know because the strangeness is -1, we know it has to have a strange quark in it. So that's first up, minus a third. Now to make the charge be -1, there's only one option really here, is that I need 2 more down quarks. So it's this quark composition of a sigma particle is strange down and down. Now for antiparticles, you also need to figure out what quarks are in them. For antiprotons, is basically the opposite of what was in a regular proton. So an antiproton has a charge of -1, and an antiproton has a baryon number of -1 as well, instead of positive 1. So if we put our anti up, and anti down, that gives us a charge of -1 and a baryon number of -1. So that fits here for our antiproton. Now, one more quantum number you need to know about, going back to our leptons briefly, is this idea of a lepton number. So just like a baryon number, if anything's a baryon, it has a +1 baryon number. If it's an antibaryon, it has a -1. If anything is a lepton, it has a lepton number of +1, and if it's an antilepton, it has a lepton number of -1. If it's not a lepton, it just has a lepton number of 0. So our electron, muon, and tau and neutrinos have +1 lepton number, and all the antiparticles have -1. The last category we haven't talked about yet is a meson. Now a meson is not a baryon, so therefore has a baryon number of 0, but contains quarks. So the only solution to that is that it has a quark-antiquark pair, meaning it's positive a third minus a third, giving it a baryon number of 0. So let's have a look at a few different common mesons and what's in them. So first of all, we've got the pions. We've got neutral, negative, and positive pions. And we've also got kaons, neutral, negative, and positive. Now, these ones, it's really useful to know. Pions don't have any strangeness, so can only be made up of up and down quarks and their anti-particle counterparts. Kaons do have a strangeness of either +1 or -1, so must have a strange or anti-strange quark in there somewhere. So let's deal with the pions first. I'm going to go right to left, just because it's a bit simpler to work out the positive and negative ones first. So positive kaons, we know it's positive, we know it's got 2 quarks, one must be an anti, so the only combination that would work with is if I have an up, so positive a 2/3, and an anti down, giving me a total charge of +1. Next, I could do the negative one. I need a -1 overall, so I do an anti up, so -2/3, and then a down, which is also -1/3, giving me -1. Now, a neutral one, you need a charge of 0. That could be an up anti up, it could be a down anti down, to give you a neutral pion. So let's deal with these kaons. Now for a neutral kaon, we know we're going to need a strange particle in there somewhere. So for a neutral kaon, that could be an anti-strange, so that would give us +1, and a down quark, which would give us a charge of 0. For a negative kaon, we're going to need a charge of -1, so that's again anti-up plus a strange quark this time, and for a positive kaon, that's a anti-strange quark plus an up, which gives us +1/3 plus 2/3, which is 1 overall. Okay, so these particles are all very unstable. They don't usually take very long to decay at all. Baryons generally are a bit more stable, like protons and neutrons, but for baryons, we've got the proton is by far the most stable one. So next we're going to look at how do these particles decay, and there are a few different conservation rules. Just like with conservation of energy, being that before and after has to be the same, in different decays and interactions between particles, there are a few things that have to be conserved. Charge has to be conserved. We also have to have the same lepton number before and after, as well as baryon number, and also energy and mass have to be conserved as well. Strangeness has to be conserved, but only in strong interactions, which we'll come on to what that means a bit later. So let's have a look at an example. So for any interaction, you could be asked to figure out, is it possible or not due to conservation rules? So let's have a look at this one here. This is a proton decaying to a neutron, a positron, and an antineutrino. So in an exam, you always want to write down below, like charge, lepton, or barrier, just do zeros, positive ones, and negative ones to show you know what you're talking about and is it conserved or not. So with a charge, we know the left hand side is +1, neutral 0, positron +1, and antineutrino 0. So charge works out fine. Baryon number, we know a proton is a baryon number, so +1 becomes +1 for the neutron, and then 0 and 0 for the electron and the antineutrino. And if we do lepton number, we got 0 on the left hand side, but we've got an antilepton and another antilepton on the right hand side giving -2. So you then therefore you'd say the lepton number, the left hand side does not equal the right hand side, so it's not conserved, so the decay is not possible. Let's look at a slightly different one. This one's involving a muon. So I've got, in terms of charge, -1 makes -1 plus 0 and 0. So that's fine. Lepton number, I've got +1 makes +1, -1 and +1, which looks like it is fine. So therefore the interaction is totally possible. So it is a legitimate interaction and decay that can happen. This is how the muon decays into an electron and 2 types of neutrino. Right, I mentioned the strong force, the strong nuclear force a second ago, so we're going to move on to talking about fundamental forces. Now, unlike push and pull and tension, these can all be explained by 4 forces that work on the subatomic level. The first force is the electromagnetic force. Now, you've come across this before. This is why 2 protons repel each other, so it only affects charged particles. You've also come across gravity before. This affects particles with mass, although particles are very, very low mass, so we won't really consider it too much here. Then we've got the 2 we're really concerned with the weak nuclear force or nuclear interaction and the strong nuclear force or interaction. The weak nuclear force affects all particles, but the strong nuclear force only affects hadrons, so leptons cannot be affected by it. So even though it only affects hadrons, don't forget hadrons can be affected by weak nuclear force because it affects all particles. So hadrons can decay by the strong interaction, but also the weak more commonly. Now, how do these forces get mediated, or how do they get exerted? This is where the idea of exchange particles comes in. The analogy to use with exchange particles are 2 people on skateboards facing each other, and one of them throws a basketball at the other. Now, if nothing else changes, the 2 people will become slightly further apart because of Newton's third law. The person throwing the ball will move backwards, the person catching the ball will also move backwards. Now, while this obviously isn't exactly what happens with exchange particles, it occurs in the same way, for example, when 2 electrons repel. So exchange particles are virtual particles that are transferred between 2 different particles that allow a force to be mediated or exerted. Now, each of these 4 forces have different exchange particles. For the electromagnetic force, it's a photon. For gravity, it's called a graviton, even though we don't really know they exist yet. It's very much a hypothesis. Gravity is a very, very weak force, so it's a lot harder to discover things about it. Then for the 2 we're interested in today, we've got the weak nuclear force, which has 3 types of boson, which it can have as the exchange particle. We can have W minus, W plus, or Z zero or neutral Z boson. And for the strong nuclear force, it can either be a pion or a gluon. Now, different decays we've looked at so far, we can represent using Feynman diagrams. So with a Feynman diagram, they look kind of scary, but they are basically just a pictorial way of showing a decay. So let's say our beta minus decay from earlier. I've got a neutron changing into a proton plus an electron and an antineutrino. So how to show this on a Feynman diagram, we go upwards to go up on in time. So we start off at the bottom, and we also make sure we kind of give particles their own space. So we start off with our neutron, it changes into our proton. We keep that on the left-hand side because it's still a hadron. And then we have our exchange particle, which kind of wiggles off to show it's a virtual particle that turns into our electron and our antineutrino. Now, in this case, the exchange particle is the W minus boson, and that's because once the neutrons change into a proton, it needs to take away the remaining negative charge for conservation of charge, which then becomes the electron and antineutrino. So this is an example of a weak interaction decay because it is affecting all particles are involved. Changing this to beta plus decay, so we change the proton to a neutron, neutron to a proton, and this time it's a W plus boson that's carrying away the positive charge to make the positron and the neutrino. Now, just a quick note on antiparticles. Some textbooks show the arrows pointing the opposite direction. It's not required for A-level specifications, but just so you're aware. Now, one last thing about Feynman diagrams, you quite often find the baryons always on the left-hand side and the leptons on the right-hand side, just to distinguish between them. So other types of Feynman diagram you can have, so when two protons repel each other, you can also represent that on a Feynman diagram, showing the two protons at the start and at the end moving away from each other, and there's a photon exchange between them to show that a force has been exerted. Now in this case, obviously you've got two baryons on left and right side. That's because there's no leptons occurring at all. Now electron capture, which is when a nucleus captures an electron from an inner shell of around the atom, is when a proton and electron we start off with, so going from the bottom, and now the proton changes into a neutron and the electron changes into a neutrino. Now in this case, the exchange particle, so between those two particles, is a W plus boson. Now please be aware, you could be asked for other diagrams than this. I would definitely learn the neutron decay, the proton decay, electron capture, and two particles repelling. But if you follow those rules, you can do it with any sort of particle interaction, really. Now, the last thing to note about the strong nuclear force is how it actually holds the nucleus together. Now, this is really fundamental to understanding why nuclei exist in the first place. So the strong nuclear force, if we were to draw a graph of the distance from the centre of the atom, so right at the centre, and put on the y-axis the strength of the force with repulsive above the x-axis and attractive below it, we find that actually the strong force is repulsive below 0.5 femtometers, and it gets attractive between 0.5 and roughly 3 femtometers, and after that basically becomes zero. So if you ever wondered why protons are held together with the neutrons in the nucleus, why don't they repel, it's because for those very, very small distances, the strong nuclear force is attractive. Now, you might be asking, well, what about the electromagnetic or the electrostatic force? Well, we're going to come to that in a second. But don't forget, the strong nuclear force is responsible for keeping the nucleus together. Now, you might be asking, well, what about the electromagnetic or electrostatic force repelling those protons? Well, that is at play as well. However, at those really, really small distances, the strong nuclear force is bigger. However, the bigger the distance you get, that means electromagnetic force becomes bigger than the strong nuclear force. So that explains why, if you have really big nuclei, they don't really survive for very long. They repel really quickly, so it usually decays or could undergo fission, and you don't get really big nuclei. There is an upper limit on how big a nucleus can be. Right, we're almost there. The last thing to talk about is specific charge. So specific charge is one of those weird equations in A-level physics you don't get given on your equation sheet, but it's quite a nice one to remember. It is the charge per unit mass of a particle. So meaning you divide the charge by the mass to get the specific charge. Charge in coulombs, mass in kilograms, specific charges in coulombs per kilogram. So you usually get asked this question of a nucleus or an ionized particle. Obviously a normal atom wouldn't have a charge, so it wouldn't have a specific charge. And please make sure you use the data sheet for all your values, for example, to work out the charge or the mass in kilograms. Now, the specific charge of an electron is much bigger than a proton because it has a much smaller mass. That's a good fact to know. The electron has one of the larger specific charges you can get, and the values for specific charge are normally in the order of about 10 to the power 7 coulombs per kilogram. Right, well done, we got there to the end. Please give this video a like if you found it useful, and look out for more for A-level physics.